Hello, and welcome to the So You Want to Be a Marine Biologist podcast, where we learn about the ocean, share sea stories, and explore ocean careers. I'm your host, Kara Muzia. Let's dive into today's episode. Hello, mermaids, pirates, ocean lovers, and land lubbers. So, you hear about mercury in seafood, and that you should be careful not to eat too much. But have you ever wondered where the mercury that's in the ocean even comes from? I did, and after a quick search engine inquiry, I found my guest today, Dr. Carl Lamborg. Carl is a marine chemist specializing in studying mercury in the ocean. Carl's research has taken him all over the world, including to the Arctic Sea and through different research institutions, such as the renowned Woods Hole Oceanographic Institute. Now, Carl is currently teaching and conducting his research with University of California, Santa Cruz. In this episode, we get into where mercury in the ocean comes from, how it gets into the food web, and ultimately, how we may have this neurotoxin inside our own tissues. Carl has a really great ask and resource at the end of this episode, so be sure to stay tuned to hear more about that. Now, without further ado, here is Dr. Carl Lamborg. Carl, thank you so much for being on and welcome to the show.
Thanks, it's my pleasure. Thanks for having me on.
So you're actually our first marine chemist to be on the show, and I'm really excited to have you on. Okay. So how did you get into marine chemistry?
Sort of by accident, I guess I would say. I was a chemistry major in college and always sort of interested in environmental kinds of things, but there wasn't really environmental chemistry when I was an undergrad, so I didn't really know that it was a thing until I sort of stumbled into it. Right after college, I just got a job completely by accident in a lab that was doing some air pollution and human health research. And I guess that's where I realized that this was environmental chemistry was a thing that you could do, and that was sort of the start of it, I guess. Yeah.
Okay. So you say air pollution. Where were you when you were studying this?
Yeah, that was in Boston at the Harvard School of Public Health. There's a group there that studies air pollution impact on human respiratory health. So there was sort of one group of people that went out and measured air pollution stuff, and there was another group of people in the same team that would go to communities then and measure the respiratory health, mostly of children in the area, and then going to many different locations around the country, and some that were very polluted, some that were not very polluted, and looking to see if there was differences between the children there. But I never did the human health side of things. I would just go and set up air monitoring equipment, that kind of thing.
How do you monitor air?
Depends on what you're looking for. In our case, we were looking for the precursors to acid rain that were the folks I was working for were looking at the precursors for acid rain, which are called acidic aerosols. So these tiny little particles that are in the air that have sulfuric and nitric acid in them. So one of the things you do is just pull air through a filter and then take it back to the lab and analyze the pH of that filter, analyze the acidity on that filter. And it will be more acidic in places that have more of these acid aerosols in them.
Okay, that makes sense. And then did your data correlate with human health issues?
Yes, apparently. I was sort of, I was very far down on the totem pole at that point. So I didn't really see the data until many years later after it had been published and that sort of stuff. I wasn't involved in that part of
Gotcha. So
data analysis.
You were in the field and collecting all the data and then
Right.
Wasn't exactly a part of the results.
Right. I was a lab grunt.
Got to start somewhere.
Exactly. Yeah. No, it's a good way to start.
It is a great way to start. So what got you interested in chemistry in the first place?
I don't know, really. Just my father was a scientist, so I sort of always knew that science was a career that one could have.
Okay.
I was sort of interested in biology, I guess, when I first went to college. And then I just remember looking at all the classes that I was going to have to take, and the chemistry classes seemed more interesting to me for some reason. I don't know why.
I mean, chemistry classes are interesting, but
Yeah.
a lot of people get intimidated by them. But you were excited by them.
I guess so. And I'm also a little squeamish. So I saw a lot of the advanced biology classes were, like cutting things open and looking at the insides of things. And I thought, maybe that's not for me. But,
Fair enough.
you know,
So you started in air pollution. How did you navigate your way to becoming in the marine world, in the
yeah.
ocean?
So after that first job in Boston, I took my first run at grad school at the University of Michigan. Also doing air chemistry things, but that's when I first started working on mercury in the environment. So
Okay.
measuring different kinds of mercury in the atmosphere. And that's one of the really interesting things about mercury is that it has this very, very varied chemistry. It spends part of its time in the air, part of its time in the water, part of its time in soil. So there's a lot of different. As a chemist, there's a lot of different things to look at there. Then, but anyway, my entree to thinking about mercury was in the air at that point. And then I decided I didn't want to keep going for a PhD at that point, and I took a job as a technician for another researcher who was an oceanographer. So that's when I first started getting into oceanography at that point. But doing
Fantastic.
mercury.
So was he an oceanographer for a university or just for
At the University of Connecticut. His name is
Okay.
Bill
So you're back in.
Fitzgerald.
Great. So that's how you kind of started to see how all your air pollution studies have kind of married into the marine world. So
Yeah,
how does mercury get into the air? Let's start
yeah,
there.
yeah. And that is sort of the way we think about when we start thinking about the mercury cycle. That's sort of usually the first step that we sort of think about. So it has both natural and anthropogenic sources. The common theme between all of those is usually some sort of high temperature process. So the most important natural source of mercury we usually think about as being volcanoes. So there's just a certain amount of mercury that's in the interior of the earth and because mercury is volatile at high temperature, when lava comes to the surface in a volcano or something like that, the mercury is able to degas, come out of the lava and go into the atmosphere. In the same way that there are a lot of other gases that come out of volcanoes as well: carbon dioxide, water vapor, sulfur dioxide. A lot of things also degas from lava along with mercury. So that's the main natural source. And then there are a slew of different anthropogenic sources. But the thing that's sort of common about them as well is that there's some sort of high temperature process. So burning garbage, for example, municipal waste incineration is the source of mercury. And also burning coal. And mercury is also used in sort of low-tech gold mining. The reason why that's a high temperature source is that in low-tech gold mining, you mix mercury with sediments or mud or something that you think might have some flecks of gold in it. And the mercury spontaneously gobbles up any gold that's present. They spontaneously amalgamate to one another. Mercury does to gold or gold to mercury. And then but this mixture of gold and mercury then is very dense and will sink to the bottom of a pan or some sort of separation system. You can sluice off the water and the sediment then, and what you're left with then is just a glob of mercury that hopefully has some gold dissolved into it. And then if you take that glob of mercury and heat it and boil the mercury off, you will release the gold that is hopefully trapped inside.
Hey, Kara here. I hear it all the time. How do I become a marine biologist? Or my niece wants to help the ocean. Where does she even start? I hear from students, yes, and also nurses, HR professionals, and other mid-career folks who wonder if they could still make their dream of working with sea turtles or sharks come true, wondering if it's too late to answer the ocean's call. Here's what I've learned after 20 years in the field and hundreds of interviews. There's no straight line, no magic degree, and no gatekeeper. You create the path forward. If this sounds overwhelming and vague, I've created 2 tools to help you stop wondering what if and start moving forward with clarity and purpose. The first is my free guide, Be a Marine Biologist Without the Degree. Over 1,000 people have already downloaded this guide and taken their first step towards ocean impact. Inside, you'll find 7 concrete, doable actions to help you get started, whether you're just exploring or ready to make a change. Then there's the Ocean Blueprint. This is a 30-day self-paced course that helps you build your unique path into ocean science and conservation without quitting your job or going back to school. Inside the Ocean Blueprint, you'll get daily prompts to explore your interests, skills, and next steps, a structure that turns overwhelm into real momentum, and a bonus section to root your work into ocean connection. You don't have to wait for a degree, a perfect plan, or permission. Whether you're wading in or ready to take the deep dive, these tools are here to help you move from dreaming to doing. The ocean called. Are you ready to answer? Links in the show notes and on my website, karagracemuzia.com. I can't wait to see the waves you'll make. Okay, so you burn this little globule and then gold is left behind. And that's...
Gold is left behind, yeah. So it's that high temperature point at that point when that releases a lot of the mercury into the atmosphere.
Okay. Interesting. So you say burning fossil fuels, is it just coal mining, or is it even, combustion in our vehicles as well?
Not really. There's not a whole lot of mercury in, I think even in crude oil, but definitely in refined like gasoline and that kind of stuff. There's not a whole lot of mercury in there. Okay. It's mostly in coal. So it's of burning fossil fuels, it's mostly coal. Natural gas also doesn't have a whole lot of mercury in it. So
okay.
It's really just the coal.
That's good to know.
Yeah.
So now mercury is in the atmosphere, yeah. And this is kind of how I found you, is you always hear about not to eat certain fish because they're big fish and they've eaten a lot of smaller fish, and right. All these smaller fish have toxins, mostly, and mercury is the main one that you hear about, that accumulate in their tissues. Right. And the larger fish gobble up these smaller fish, and then they accumulate even more toxins in their tissues, and it's a process called bioaccumulation. So I wondered, where does the mercury in the ocean even come from? And that's kind of how I found you. Yeah. So how does it get from the air and from burning fossil fuels into the ocean?
Yeah. So most of the mercury that does end up in the ocean does come from the atmosphere, though there are small contributions from mercury that makes it into the ocean through rivers and groundwater, and maybe even from volcanic activity that's taking place in the bottom of the ocean, submarine volcanism, as it's called. But the majority, we think, comes from the atmosphere. And so in the atmosphere, so this is where we have to wade into a little bit of chemistry for this to all sort of make sense.
Okay, got my waders on, got my boots on.
Okay, good. So the form that's in the atmosphere is mostly elemental mercury, which is the same stuff that's in thermometers. It's the white metallic or silvery metallic kind of stuff. Mm-hmm. But it is weirdly, compared to other metals, it's fairly volatile. So it can actually hang around in the atmosphere for a little while. People talk about a lifetime in the atmosphere for elemental mercury of something like 6 months to a year. So once it's up in the air from one of those processes we just talked about, it's able to be dispersed globally in the atmosphere, but it's slowly being removed through a process called oxidation, where it is converted from elemental mercury that has a 0 charge on each mercury atom to the mercuric ion, which has a +2 charge on each mercury atom. And as the mercuric ion, it's much less volatile. And so it will start to fall out of the air. Usually, once it's in this ionic form of mercury, it's going to quickly dissolve into raindrops, into clouds. It's going to stick to dust that's in the air. Its chemistry is much more reactive once it's in this form as compared to when it's in the elemental form. And so it will just be naturally sort of scrubbed out of the atmosphere. along with a lot of other stuff. There's many other chemicals, for example, in the atmosphere that are removed in the same kind of way. So it's a natural process that removes it from the air.
Okay.
Yeah. And then it falls in the ocean. After it's removed from the air, a lot of it falls directly onto the ocean.
Okay. So it's literally just raining mercury on our oceans all the
Yeah.
time.
Yep. Absolutely.
And then just
And then
through.
once in the ocean, so it's now you've added the mercury to the ocean in this mercury +2 form.
Mhm.
And the kind of mercury that you find that's in fish is a third kind of mercury, which is called methyl mercury.
Right.
And so the amount of the mercury that enters the ocean is really a tiny, tiny percentage of it is this methylated mercury form. And so essentially all the mercury that ends up in fish has to have gone through another kind of chemical reaction where it becomes methylated. And that has to take place somewhere in the ocean through some sort of process before it can be accumulated into a marine food web, including the fish.
Okay. So I have two questions. How much mercury is really released into the atmosphere, and does it become an issue? Like, is it automatically mean that we're going to be seeing it in the ocean?
Yes, we will automatically see it in the ocean. It's just a matter of how much.
Hmm.
And to be clear, before people were around, 2, 3, 400,000 years ago, something like that, there was mercury in the ocean then as well.
Right.
It's just that, and mercury, of course, it's an element. It's been around. It's been in the planet and moving around the planet since the planet was formed.
Hmm.
Um, so we're not creating any new mercury. What we're doing is we're just digging it up out of the ground essentially and throwing it up in the air and allowing it to start moving around. And so there's more mercury moving around at the surface of the earth, including in the oceans, today than there was before people started doing these industrial type activities.
Gotcha.
To the tune of something like, well, there's some arguments that go on between mercury nerds, but it's something in the neighborhood of 3 to 7 times more mercury moving around the surface of the planet today than there was 500 years ago, let's say.
That's a lot.
That's a lot. Yeah. And so we think, although this is still kind of an outstanding research issue, is that we would then assume, we would predict then that maybe fish have gone up by some similar amount, that there are like 3 to 7 times more mercury in fish today than there was 500 years ago, something like that. Though there might be reasons why it wouldn't, those two kinds of numbers wouldn't perfectly track each other. And
Hmm.
so there's a lot of research going on trying to figure out if that's really true and why it might be true, why it might not be true, and that sort of thing.
Have there
But
been any preliminary results about that?
yeah, so it's a little hard to go back. For there was an effort a few years ago, for example, to go back and look at, say, fish that were in museums and see if the fish that were caught, a few hundred years ago or something like that, had less mercury in them than today. And that always gave these sort of strange equivocal results because probably the fish samples became contaminated with um, mercury from hanging around in the museum. Mercury is sometimes used as a preservative to keep things from
Hmm.
rotting. Um, and also, it's true that the amount of mercury that's out in the ocean, I think you were sort of maybe you were starting to ask this kind of question. The amount of
Hmm.
mercury that's in ocean water is really, really small.
Yes.
Um, and so it doesn't take, and the amount of mercury in fish is much more. So this is a consequence of what you were saying at the beginning, this idea of bioaccumulation of mercury. Um, but the amount of mercury in the fish directly is sometimes, especially for smaller fish, is not super, super high. And so it is still possible for us through our handling and for the fish hanging around in our industrialized kind of world, for the samples to become contaminated with extra mercury that they didn't have when they were swimming around in the ocean. Um, and this is a process. There was exact same kind of story occurred when people were really trying to study lead in the environment in a very serious kind of way, and they realized that we, the scientists and the people collecting the samples and that kind of stuff, could be serious sources of contamination And the numbers were coming back even higher than they were out sort of naturally out in the world. And there were a couple of people, including Claire Patterson, who was the person who figured out the age of the Earth using isotopes of lead in meteorites, was one of the first people to recognize that we have to be really careful about how we collect these samples and store them and all this kind of stuff to avoid contaminating these environmental samples.
So is there a way to do that?
Yeah. So one of the things is you have to clean especially when you're trying to collect seawater to measure mercury concentrations. You have to clean the bottles very carefully and do the cleaning inside of a clean lab and process the samples in a clean lab, where you're careful to wear gloves and cover your clothes with a jacket and maybe put on a hairnet or something like that, so that you don't have little pieces of dust that sort of come off of your clothing and your hair and that kind of thing and fall into your sample by accident. Yeah, I don't know.
So you're truly like, I mean, completely kitted up in like gas masks almost.
Yeah,
to try to make sure it's all sterile and reduce contamination.
Almost.
I'm kind of picturing like Breaking Bad without the gas mask.
A little bit, actually. It's not too far. And mercury is one of these quote unquote contamination prone elements that chemical oceanographers are spending a lot of time studying. The more important of which, perhaps, or the more heavily studied of which, are things like iron and zinc in the ocean. And those you have to be incredibly careful about. You can imagine, for example, going to sea and trying to study iron. Meanwhile, the ship itself is this big hunk of steel that's sort of rusting away in seawater. So there you have to be incredibly careful about how you collect the samples so that you don't contaminate them. Mercury is not quite as contamination prone as some of these other elements, but it's you still have to be real careful about how you collect things.
So how do you collect mercury samples?
Yeah. So with very clean bottles, we go to sea, and we lately we've been going to sea with these other people who are collecting these other what are called trace elements in the ocean.
Mm-hmm. And mercury is one of them.
And
what are some of the other trace elements that they're looking at?
Iron, zinc are two very important ones. Iron is a very important micronutrient for all phytoplankton in the ocean, and can be limiting. There's certain parts of the ocean where phytoplankton can't grow as much as they'd like because they don't have enough iron. Zinc is another one that's also very important that we all use, including you and me, for a lot of our enzymes. If you look at the side of a cereal box or on your vitamin bottle, it's all the things that you see there. So it's things like iron and zinc and cobalt and manganese and selenium and sort of copper, a few other things that I'm sort of blanking on at the moment.
Okay, so there's quite a few trace elements that other people are looking at.
Yeah, right. So we go to sea with them, and we put this system called a CTD rosette over the side of the ship, and which allows you to collect water at different depths. And as soon as that collection system comes back on board, you grab the bottles and you rush them into a portable clean lab, which is inside of a 40-foot or 20-foot, shipping container that's bolted down to the ship. And the reason why we want to do it fairly quickly is that there's a whole lot. Not only the ship is rusty, there's also all these gases with lots of dust and soot and all this kind of stuff coming out of the smokestack of the ship. So we want to protect the samples from all that kind of stuff as well. So we hustle them into this clean lab and then very carefully decant the water out of these bottles and in this clean.
And the water samples are taken at different depths, correct?
At different depths. That's right. Yeah.
Okay.
And then there's a team of people that are collecting the water samples, and then we all give them our very carefully cleaned bottles. They fill them up with water, and then they give them back to us, and then we begin to analyze them.
How do you analyze that?
Yeah, mercury and seawater is analyzed using a measurement technique called cold vapor atomic fluorescence spectrometry.
Okay.
Mercury is sort of unusual in that it will absorb and emit UV radiation. So if you shine, actually the inside of each one of the fluorescent, you probably have fluorescent lights in your office somewhere.
Hmm.
Um, those have a fair amount of mercury inside of them, and when that gas is the mercury gas inside the fluorescent tube is zapped with an electrical charge, it the atoms get excited, and then when they begin to relax, they release UV radiation. Their UV radiation coming off the mercury then hits the coating on the inside of the fluorescent tubes and makes them glow the sort of white, visible light color um, that we actually see. But fluorescent tubes actually emit a fair amount of UV radiation as well.
Hmm.
So it's a little bit, what we do analytically is a little bit like what goes on inside of a fluorescent tube. We shine UV radiation at the mercury atoms in a sample. They absorb some of that radiation and then they release it again. And so we watch for how much UV radiation is given off by the sample.
Okay.
And it sounds complicated. It's actually fairly simple. It can be done with a fairly small analyzer. And so we usually do most of our analyses at sea. We take all of our equipment to sea because it's not super big or really complicated in the end. One of the steps that we do this is kind of a little bit ironic is we have to pre-concentrate. We have to sort of collect all the mercury out of one sample and analyze it all at once. And we do that by degassing the mercury out of the seawater and then collecting it on gold. So it's actually, the chemistry there is the reverse of what gold miners are doing. They use mercury to trap gold, and we use gold to trap mercury. Yeah.
That's fantastic. So you bring your gold chains as well as your spectrometer onto the boat.
That's right. Yep. That's right.
So I kind of read a couple of the abstracts. You've traveled all over the world, looking at mercury in the oceans. I mean, the Arctic Ocean, the Atlantic, Pacific. What does that look like? Southern Ocean?
I haven't been to the Southern Ocean personally.
Okay.
But they all look, it all kind of looks the same when you're out there. It's
so where are you flying into different places? I'm assuming you're not leaving out of California. And then how far offshore are you going on these expeditions?
It's real variable. It depends on what the project is exactly looking at. This one that I said that we've been going out to sea with these other trace metal oceanographers. The whole point of those cruises is to sort of cut a big swath through large major sort of basins of the ocean. So we went straight across the North Atlantic. We went west from Peru across the middle of the equatorial Pacific. We went from all the way into the open Arctic Ocean and back again. And then the latest cruise, which I didn't go on myself, but folks went from Alaska all the way down to Tahiti through the North Pacific into the equatorial Pacific and then into the South Pacific. But then also some of the recent cruises I've done have been just sort of within sight of land in the coastal ocean as well. So there's a mixture of things. Depends on what the project is designed to kind of look at. Sorry to follow up on what you asked earlier, you meet the ship wherever it is. They usually have a home base, or in the case of the ships that sort of cross wide chunks of the ocean, you meet the ship wherever it stopped after its last cruise, after the last leg of its work. And then you meet it there, and then you go off and do your thing. And then you get off, you load all your equipment onto the ship at the beginning. You transit the part of the ocean that you want to study. You end at some ending port. And you take all of your stuff out of the ship and leave. And then a whole new troop of scientists show up and load all their equipment onto the ship and do their thing then for another leg. So then the ships that do the really big open ocean kind of work may not be at their home port for a year or something like that, and they're just sort of zigzagging around the ocean.
Incredible. So is there some sort of like network that you can kind of tap into and like pick which ship just based on like where it's going and what availability there is?
Yeah, there's a network called UNOLS, which I forget what the acronym stands for, but these ships they're not a huge number of them. There's about I think a half a dozen or 8 of the really big open ocean going research vessels these days. It's not in the United States.
Hmm.
Um, and each country has their own. And the ships are very expensive to operate, as you might imagine. So a lot of them are actually owned by the government or owned by the Navy. And
Mm.
then different oceanographic institutions around the country operate them or do this sort of the day-to-day sort of, they drive them, they put the crews on them, and the crews take care of all these different kinds of things, but they don't actually own the ships in most cases. And so there's this network called UNOLS that when you put in a grant application to go on one of these cruises, at the same time you fill out a form that says, I want to go on, I want ship time, and I want to go from here to here, and that's going to take me 10 days or a month or something like that, and I need, because of where I'm going, I need a ship of this size. Um, and then if you get funded, it's the job of UNOLS to sort of figure out how to make that happen and find you a ship that fits your needs, and that sort of thing. And sometimes you have to, because there's the community of American oceanographers are all vying for time on these ships, and there's usually sort of more time is asked for than the ships actually can provide each year. There's always a little bit of compromising and sort of horse trading that goes on to figure out how to get everybody most of what they want, and that sort of thing. And sometimes you have to wait a little. You might have to wait an extra year or something in order for your chance to go out on a boat to come up.
Right. If there's
Will happen.
zigzagging all over the planet, you may have just missed your port.
You may have just missed your port, yeah. And so sometimes it's good to be flexible, and sometimes you can't be flexible. It's like, no, I have to go to this particular part of the ocean at this particular time of year, and I need this ship to do it, and that sort of thing. For example, if you are an oceanographer who studies deep sea hydrothermal vents, for example, you
Mm.
need to go out on a ship that can support, say, Alvin, one of these human
ROVs.
operated submersible things, or maybe you can use a robot, one of the ROVs, the remotely
Mhm.
operated vehicles. But the ships that can support those things are even fewer. I think there's just one ship that can support Alvin, and there's maybe 2 or 3 ships that can support the ROV work, I think.
Did there used to be more?
There did,
Like
yeah.
dwindled?
Yeah, the size of the American scientific fleet is shrinking.
Mm.
Yeah, there's just
Okay.
not enough support for science in general, but including oceanography in the United States these days. And so to sort of cut costs, we've had to mothball a few ships. Or I should say, when they sort of when ships have reached the end of their lives, they haven't been replaced.
Okay. You just get
Yeah.
scuttled to become artificial reefs or otherwise repurposed.
They usually get sold to other other people for other
Okay.
trips. So they're out there probably driving around doing something somewhere in the world, but just not part of
Okay.
the American scientific fleet.
All right.
I guess
What's long?
at some point they probably get chopped up into scrap metal.
That or that too.
But
What's the longest you've been out at sea?
yeah, this Arctic Ocean cruise is the longest one for me. That was just over 2 months.
Wow. What time of year were you there? I mean, either way, it's cold.
It was pretty cold. So we wanted to go. It's easiest. So we were on the United States only science supporting icebreaker, which is the Coast Guard cutter Healy. So it's a
Hmm.
Coast Guard boat actually. Whose home port is in Seattle. The U.S. really has only one icebreaker at the moment. So if you want to do anything in the Arctic Ocean where you're going to encounter any kind of ice, you have to go out on the Healy. And the goal was to try and make it all the way to the North Pole. So to make things
You
easy
see
on
Santa
yourself,
while you're up
then
there.
what's that?
You see Santa while you're up there too.
Well, we did in a way. We did actually.
Oh, okay.
That's an interesting and very heartwarming story. Um,
Okay.
but you have to go when the ice extent is at its smallest to sort of make it
Right.
easy on yourself, and that's September. So we our goal was to sort of get to the North Pole in mid-September. So
Okay.
it was sort of late fall that we left Seattle, or actually we loaded the ship in Seattle, and then we met the ship later to actually start the cruise in Dutch Harbor, Alaska, which is out on the Aleutian Islands. The Santa Claus part comes actually. So we're out when we got to the North Pole. Some of the Coast Guard crew had brought with them a pole, like a barber's pole kind of thing, which they carried, and also a Santa suit. And so they went out and posed, pretended to be Santa, and had got their took pictures of Santa receiving letters from the children of the people that serve in the Coast Guard. So that was really cute.
Oh, that's fantastic.
Yeah, yeah, it was really wonderful.
I love it. Science with a sense of humor.
That's right.
Makes me
That's right.
smile. It's
Yeah.
fantastic. So that kind of leads me into one of my favorite questions to ask
Yeah.
is what are one of your or a couple of your favorite field story or stories to tell? It could be like the most amazing day possible on the ocean, like everything went right, or it could be like this thing happened and this is how I overcame it,
Mm.
and now I'm happy I can tell a story about it and I'm glad it's over.
Mm. Wow. Gosh, I don't know. I don't have any really fantastic stories in that respect. I had some real, so that Arctic
I'd
cruise
love
was really
to.
wonderful in that I think the main thing that I've really liked about all these things is that I've got to go to some places that I'm sure I wouldn't go, that are really beautiful, but that I probably wouldn't have made it to as just a regular tourist, you know.
Mm,
So the Arctic Ocean is certainly one of them,
mhm.
and getting to see all that and the wildlife and that sort of stuff was really amazing. And coming back, there were some evenings. So as we were heading up there, it was essentially 24 hours of sunlight. By the time we came back, it was getting dark at night, and we would see the northern lights like right over the ship, and all that was really
It's
really
magical.
really pretty amazing. Yeah, and going to sea in general is sort of magical in that sense, in that you're far from light pollution, so there's always amazingly starry skies, and sunsets and sunrises are always really pretty spectacular. The downside, I
Would
guess, then going to sea, of course, then are storms. So I don't normally get seasick, but there was one storm that was pretty bad. I did a fair amount of work off of Bermuda for a few years,
mm.
um, and we
And the
got caught
Bermuda
in
Triangle?
yeah, technically.
All right.
Um, it wasn't a hurricane, but it was a pretty big storm with some pretty big waves. And these ships are completely, it would really take a lot to actually put the ship in danger, but it can be extremely uncomfortable, where you have to sort of wedge yourself into your bed you can't work under those conditions. It's really, it would be incredibly dangerous to be out on deck. And so they just sort of lock all the doors of the ship, the watertight doors of the ship, and then everybody just sort of hunkers down and tries not to throw up, basically. So that's a little unpleasant.
Yeah,
An
no, I guess
unpleasant side of oceanography.
right. How big was the ship that you were on?
That one was a sort of medium-sized ship. That's the Atlantic Explorer. That one, I can't remember the numbers. It's on the order of sort of 150 feet long, I think.
Okay.
So,
So some big waves to throw a boat that size around.
yeah, for sure.
Would your collegiate self have believed that this is kind of where your career in chemistry was going to go?
I don't know. I don't think so. That's a good question. No, and as I said when I started, I didn't think I was, oceanography wasn't really on my radar. Sort of backed into it, but the field work in general is a lot of fun.
Yeah, always is.
Yeah.
Kind of wanted to circle back to Mercury, and
Yeah.
now we have Mercury in the ocean in its 2+ form.
Right.
And you mentioned there's different processes that will get it to convert to the methyl mercury.
That's right. Yep.
So what I read, it takes like a bacteria that actually converts it, or are there other processes?
Well, this is the sort of hot topic. So we know that bacteria can do it. We just don't know if the bacteria that we know about are the ones that do it in the ocean. And the bacteria that we know about are bacteria that live in environments where there's no oxygen. So you and I and all the whales and fish and lizards and birds and all this kind of stuff are all critters that need oxygen to live. We burn our food, we eat food, and we burn that food for energy, and the way we burn that food is using oxygen. So we're all essentially sort of low temperature flames. The same kind of chemistry is going on inside of a fire. Oxygen is reacting with organic matter and releasing energy. We just do it very, very slowly, so we don't spontaneously catch on fire. But there are and that's the only kind of way that we can survive. But bacteria can survive on things other than oxygen. And there's some critters that actually can survive on oxygen and non-oxygen things. So there are a whole group of bacteria out there, for example, that we breathe oxygen. These bacteria breathe sulfate, which is a salt that's present in seawater. And they're called sulfate-reducing bacteria. So they eat organic matter that they find in sediments, and they burn it with sulfate instead of with oxygen, which is a wholly alien way of life compared to what sort of the way that we think of that our lives are like, and that most of the animals and critters that we sort of see in our everyday life. So it's really, bacteria are have incredibly very different ways of living compared to us. We can only really do one kind of chemistry, and they can do tons of different kinds of chemistries. And one of them is this sulfate reducing trick. And we know that these critters that live in environments without oxygen, things like sulfate reducing bacteria and iron reducing bacteria, contain a gene in their genomes that will methylate mercury. So just sort of during their workaday lives, they're methylating mercury. And we think they do it by accident. We don't think they're doing it on purpose for any particular reason.
Okay, so it's just kind of a byproduct of their regular processes.
That's right. And not all bacteria that live without oxygen do it. Some, and even two different bacteria in the same sort of family of bacteria, one will methylate mercury and one will not. It's that part of the sort of the ecology, the microbial ecology of mercury methylation is still a big area of research, trying to understand why some have this gene and some don't have this gene. But so every kind of bacteria that's been found, and actually there's a whole other family of microorganisms that are not bacteria. They look a lot like bacteria, but they're not. They're called archaea. And they are as different from bacteria as you and I are from bacteria at a genetic level. So under a microscope, they look pretty similar, but genetically, they're also radically different. But this same gene has been found in some of those organisms as well. But so far, all of the bacteria and archaea that have been identified that possess this kind of gene have to live in environments where there's no oxygen. So that is very commonly found, for example, in the mud at the bottom of the ocean, and in the mud in the bottom of lakes. And actually, deep in soils, you find the same kind of situation as well. But the ocean is a location where there's really usually quite a bit of oxygen. There are some parts of the ocean that don't have a whole lot of oxygen, but those are sort of unusual places. And we know that mercury is being methylated in places where there's plenty of oxygen in the water. So we don't really, that's a big puzzle right now, actually, that we're trying to figure out. Are these same kind of bacteria that live in no oxygen present inside of little particles that are floating around in the water, where there's maybe no oxygen on the inside of the particles? That's one possibility. Another is that maybe there's just a whole other way of methylating mercury with bacteria that have a completely different gene than the one that's been found in sediments. So we can measure the rate at which mercury is converted from inorganic mercury to methyl mercury, but we don't necessarily know what's going on down at the molecular biological kind of level yet.
Wow. So there's still a lot of unanswered questions with this.
A ton, yeah.
Interesting.
Like really basic stuff too.
Right. So we know that once it's converted to methyl mercury, how does it do phytoplankton kind of absorb it? And is that how it works its way into the food web? Like, how does it get into where it affects humans more?
Yes, it gets in first from phytoplankton.
Okay.
How it actually does that is also a bit of a mystery. Right now, it looks sort of just like it diffuses in. So methyl mercury likes to be inside. It is lipophilic, is the technical term. It likes to be inside of living tissue rather than floating around in seawater. So it will just sort of naturally gravitate towards dissolving into phytoplankton. That we know is true. We don't know if that's the main way that methyl mercury ends up in phytoplankton, or whether are actively taking it up out of the seawater or not. That's another possibility. There's a fair amount of research being done on that. But what's pretty clear is that once it's inside the phytoplankton, it's sort of a fait accompli, that then when zooplankton come and eat the phytoplankton, they will hang on to most of the methyl mercury that was in the phytoplankton cells that they ate. And then when a fish eats that zooplankton, it will hang on to most of the methyl mercury that it ate out of that zooplankton, and then larger fish, and then top predators, sharks, marine mammals like sea lions and so on and so forth, and people at sort of at the top of the marine food web.
Okay.
Yeah.
So if we're swimming in the ocean, there's mercury present, and it may or
Yep.
may not be methyl mercury, but in that state, could it hurt us, or is it only when we ingest it?
Only when you ingest it. It's the concentrations in seawater are so dilute that it can't possibly harm you. Already, so we talk about the bioaccumulation is the process of the methyl mercury wanting to go from seawater into cells. And then
Mm-hmm.
there's another process technically that's called biomagnification. It's sort of
Mm-hmm.
closely related, and the terms are often used interchangeably.
Mm-hmm.
But the biomagnification process is the fact that every step you go up a food web, every in a trophic step you go up in a food web, the mercury concentration gets higher and higher. So already the concentration of mercury inside of phytoplankton is already about 10,000 times greater than the concentration of mercury in seawater. So that's a
Okay.
huge concentration step just right there. And then there's about a factor of 10 increase in that concentration every time you go up a trophic level in a food web or food chain in the ocean. So by the time you get to something like tuna, the tuna will have something like 1,000,000 or 10 million times more mercury in their flesh than the water in which they're swimming as a result of the methyl mercury flowing up through the food web. So you can see there that it's, oh yeah, you don't have to worry about the water. The water is super dilute. It's the tuna you have to worry about. It's the fish that you have to worry about.
Mm-hmm.
The form of mercury that does this most dramatically is this methyl mercury form. So in seawater, methyl mercury is maybe a few percent of total mercury that's floating around in the water, but by the time you get to a tuna, it's 100% of the mercury that's present in tuna is this methylated mercury form.
Okay. And this is the form that can cause all sorts of human health issues.
Yeah, all forms of mercury are toxic. It's this methyl mercury form that just sort of hangs around inside of living tissues that our bodies have a really hard time getting rid of. If you were to ingest some of the inorganic, the mercury 2 plus salt, the ion,
Mm-hmm. So
your
before the bacteria get a hold of it and turn it into the methyl mercury.
that's right. Your body can get rid of that pretty quickly. It's pretty good at detoxifying that kind of mercury. But the methyl mercury form sort of gets up into the fat and nooks and crannies in your body, and your body just has a hard time of getting rid of it. It actually has to demethylate it first and then get rid of it as non-methyl mercury.
So in certain concentrations, your body can get rid of it.
Yeah. And so actually if you are a fish eating person, you probably have a lot more mercury inside your body than a non-fish eating person. And if you stop eating fish, the mercury concentration in your body will go down over time. Your body does have a way of getting rid of it. The problem is if you eat fish and therefore eat mercury faster than your body can get rid of it, the concentration in your body will go up over time.
Do we have any idea that kind of the metabolic rate of that process?
Oh gosh, you would ask me that question. That's a number I should know off the top of my head. I know that. So one of the target populations that public health people really want to reach out to are pregnant women, because mercury is a neurotoxin, and children and fetuses have developing central nervous systems, and mercury can get in there and mess up the development of a central nervous system, and it'll be irreversible. For adults, for example, some of the toxicity of mercury is reversible to some extent, but for a fetus or for a child, it can be irreversible. So public health people are particularly worried about trying to lower the mercury exposure of pregnant women, for example, and so the public health officials will suggest, if you can pull it off. I mean, I realize getting pregnant is not always something you can easily plan, but if you're thinking about getting pregnant, you should stop eating fish for something like 6 months before you want to get pregnant, just to give your body a good flushing to get rid of all the mercury that it possibly can. So that probably means that would be, that's probably based on like 3 or 5 half-lives of mercury in your body. So a half-life of mercury in your body might be something on the order of a month or 2, something like that.
Okay.
I'm guessing. Don't quote me on that.
So say you ate tuna every single day for 6 months.
Yeah.
Or, every single day for years even, and
Yeah.
then, if you waited, then you cold turkey didn't eat any fish.
Right.
If you wait 6 months, it'll definitely decrease, but would it be completely gone?
It
Do we
won't
know?
be completely gone. It's one of these exponential decay kind of curves. So it will have dropped enormously. It will be 95%. It'll be only 5% of what it was when you stopped eating fish.
Okay. But
So
then
if
that
you were
last
a person who ate if you were a person who ate a ton of fish all the time, and then you went cold turkey, after 6 months, your level still might be higher than somebody who was a vegetarian, for example, and never ate fish. But if you continue to wait, if you continue to not eat fish, the concentration will continue to go down and down and down
Okay.
over time. Yeah,
Interesting.
it's really quite dramatic. At some conferences, for example, there's a company that sells a machine that will measure mercury in hair very quickly, and
Oh.
so both me and my vegetarian grad student, for example, gave them hair samples to analyze, and and I'm not even a very avid fish. I mean, I like fish, but I don't eat it super regularly. But the concentration of mercury in my hair was, I think, 10 times hers or something like that. And she's vegetarian.
Interesting. I was gonna ask, so you still eat fish?
I do, yeah. So men, we have it easy in many ways, and one of the things is that we can eat a fair amount of mercury in fish, and therefore get a fair amount of mercury before it will really harm us. An adult man, for example.
Hmm.
So a lot of the public health concerns that one sees out in the world are really targeted towards children and pregnant women. So
Okay.
men have it a little bit easier than women in this respect, in that we can probably more safely eat more fish than and an adult woman who's not planning on getting pregnant also can also eat almost as much fish as they want. Um, there are health concerns though for pregnant women and children. So when you read these health warnings, for example, they suggest not eating fish that have more than about a half a part per million mercury in their tissues, more than say maybe once a month or something like that. Those health warnings are directed mostly towards pregnant women and children. Um, Adult men and women who are not about to have children can eat a fair amount more without being at risk. But there are levels at which if you ate more and more and more mercury, you would be at risk of some neurological damage for sure.
All right. That's really good information to know. So I want to kind of revert back to the ocean science part.
Yeah.
Do you have advice for anyone that would wants to become an ocean scientist, or any advice that they should ignore?
Uh, Ignore. I don't know that there'd be anything that should ignore. If I'm a positive story in any regard, it's that you can be an oceanographer even if you sort of don't start out as one. I don't think you necessarily need to. I was not the kind of person who sort of dreamt of being an ocean scientist all my life, and I did extra after school activity. I mean, I grew up in Ohio, also in the middle of the country. Um, so just because if somebody's listening to this and they want to be a marine scientist and they live in Kansas, don't despair. It's certainly possible. Um, and I think the best advice is probably to get a really good education in some sort of basic science, like biology or chemistry or physics or geology, and then look for opportunities to be a marine scientist after that. There are certainly programs, and maybe you're a product of one, where you can get degrees in ocean sciences as an undergraduate, for example. They're not
Actually,
super.
my degree, we had lots of upper level electives that were marine related, but
Oh,
I took them all. But my degree is actually just in biology.
and just in biology, yeah. I mean, I think that's maybe your experience is maybe the sort of the ideal one, which is get a really solid grounding in one of the basic sciences, and then but try and get as much exposure to ocean science stuff as you can if possible. But even if you can't, I came up at a time when, I mean, I didn't take any oceanography as an undergraduate. So it's certainly possible if you You don't have to have been kind of working on this every waking moment as a child, for example, to become an oceanographer. I'm sure you can, if you are keen to become an oceanographer and you already know it, that's great too. But there's certainly paths to this as a career that don't require you to be raised in Florida or California or wherever and by the ocean and, swimming in the ocean every day of your life or something like that. You know what I mean?
Right.
So I think a good solid grounding in one of the STEM fields is probably the best initial advice for any kind of career in science.
Okay. One of my favorite questions to ask. What's your favorite sea creature? And I'm very curious to ask this question of an ocean chemist.
Yeah, boy, my experience is pretty limited.
Okay.
One thing that since I moved to California, that I've been doing is teaching an intro oceanography class to undergraduates. And we try and go to, there's some tide pools nearby.
Those are always fun.
So that's pretty cool to look at all those.
Tide pool critters.
Sea anemones still sort of amaze me. I think those are really pretty incredible.
Why do they amaze you?
I don't know. They just look they're so, well, I guess all marine life, you know this in spades, but all marine life is just so alien, to a person who sort of grew up walking in temperate woods in North America. All sea life seems sort of incredible and strange and sort of alien on some level. And anemones look particularly crazy and alien to me for some reason.
They do. They do look like very otherworldly.
Yeah.
Fantastic.
I don't know if that makes them my favorite, but I definitely enjoy looking at them. And a lot of tide pool creatures in general, I think are really fun to look at.
Tide pools are wonderful things.
Yeah. I'm also a birder, so I also enjoy, that's one thing that you get to see when you're out to sea, that you don't get to see when you're, on land really, are seabirds. I think seabirds are also really pretty incredible. A lot of them, spend large chunks of their year out in the open ocean, never touching land. And
that's one of my favorite seabirds are frigates.
Mm-hmm.
They're fantastic. What's yours?
We have a lot of pelicans here. I think pelicans are really cool. They also look they look like flying dinosaurs to me as well.
They kind of do. They definitely have their own personality as well.
Yeah.
So there's a couple things as we wrap up here. I always like to do an action item or a conservation ask for the audience. And you said that you had one.
Yeah. So I don't know. It's not a big deal really. And I'll give you a link to a page that will help folks do this if they want to do this, which is just to go and spend some time looking at the concentration of mercury in different kinds of fish and sort of spend some time thinking about your fish intake as a consumer and what that might mean in terms of your mercury exposure. So one way to deal with that, if you really like to eat fish, and fish is also, wonderful source of low fat protein and omega-3 fatty acids, and it's certainly a good part of anybody's diet, is to think about eating lower on the food chain. So instead of tuna, think about flounder or something like that, because fish that live lower down on a food web will just naturally have less mercury in them. But I think it's a hard thing to sort of internalize unless you spend a little bit of time looking at a sort of list of fish to eat and fish to avoid. And there's the Monterey Bay Aquarium, for example, puts out a listing of some of these things. So I'll try and find a link that you could post to your website. But
absolutely, yeah, I'll put a link in the show notes for the Monterey Seafood Guide as well as your interactive website. That's great. Learn more all about it.
Yeah, right.
If listeners want to find you or your research, where's the best place to find you?
I guess at the University of California, Santa Cruz Department of Ocean Sciences. I have a very modest web page there, and my email is there, and other ocean scientists that people might be interested in.
Do you have any final words or pearls of wisdom you'd like to leave behind?
No, just I think this is great. What you're doing is wonderful outreach. Yeah.
Thank you. Well, thank you for being on the show, Carl.
My pleasure.
Thank you for listening to today's show. As always, all the show notes, including Carl's ask, is over at marinebio.life. You can find the show notes for this specific episode at marinebio.life/Carl. I'd love to hear any insight you've gleaned. Did you learn something new? Do you now want to be an ocean chemist? Leave a comment in the show notes or send me an email over at marinebio.life. If you enjoyed this episode, subscribe and, of course, share with your friends. Keep after your dreams and making waves in your community. One person can make a difference. One more thing. Have you checked out the So You Want to Be a Marine Biologist Patreon page? Patreon is a marvelous site that allows creators to be supported by their audience, you. We have some ocean-tastic categories for you to join, from foundational phytoplankton to enigmatic sea turtle. There's some exciting bonuses on there, from shout-outs on the podcast to bonus episodes that only you will get. Your support helps to create more episodes about ocean science and conservation. For more information on how you can be an official member of the Marine Bio Life pod, please visit patreon.com/marinebiolife. Thank you for listening to today's episode. If you enjoyed it, please take a moment to subscribe to our channel. It helps other ocean enthusiasts find us. And we'll catch you next time on the So You Want to Be a Marine Biologist podcast.